here, also from Hebrew University, to give us part 2 of local testability in group theory.
Thank you very much. I will focus on positive results for amenable groups. First, I want to say that regarding negative results, then all the negative results that we have for amenable groups, they hold even for the extended notion of testability that Alex mentioned earlier. Only the negative result for property T is sensitive to whether or not you are adding a vertex or not. Okay, so we have a set of words over some alphabet of letters and their inverses, and we have 2 points of view on this set of words, either a system of equations, each word equals 1, or as a presentation of a group taking the letters as generators and the words as relations. And this is just to fix a notation. We have the substitution. If I have a word, wi, and d permutations, sigma 1 up to sigma d, then I denote by wi of sigma 1 up to sigma d the permutation resulting from this substitution, taking the letter t1 to sigma 1, t2 to sigma 2, and so on. So I'll denote it like this. And I'm fixing the Hamming distance on the symmetric group, which again means that the distance between a permutation sigma and tau is the number of entries for which they differ, divided by n, so the distance is always a number between 0 and 1. If I have such d-tuple of permutations, then, well, I have the notion of a solution to the equations, which is just, I say that the tuple is a solution if substituting it to each of the words gives me the identity. And an approximate solution, a delta solution, is a tuple when substituted into the words gives me almost the identity. So the distance between each word after the substitution and the identity is smaller than delta. That's a delta solution. And I have the notion for 2 tuples, sigma 1 up to sigma d and tau 1 up to tau d, I have the notion of them being closed, epsilon closed. I say that they are epsilon closed if the distance from sigma 1 to tau 1, sigma 2 to tau 2, up to sigma d to tau d, together is at most epsilon. Of course, it doesn't really matter if I take it together or each one of them, but this is more comfortable for proofs. So I'm counting the number of changes I need to do all together to get from sigma 1 up to sigma d to tau 1 up to tau d. That's how I measure distance between tuples. And the definition of a locally testable system of equations is that this system, w1 equals 1 up to wr equals 1, is locally testable if for every epsilon there is delta, such that for every size of permutations, no matter how large, every delta solution is epsilon close to a solution. Yeah, that's the same definition Alex gave. And we also have the group theory point of view, that in this same situation of a locally testable system of equations, we say that the group presented by those equations as relators is locally testable, and this is independent of the presentation we choose. Yes, if 2 presentations give me isomorphic groups, then either both are locally testable as equations or both are not. And when I'm talking about locally testable groups, I will always only consider finitely presented groups. Okay. And now I'm starting with something new that was not in Alex's talk. I want to translate the problem to the language of graph theory, the theory language of labeled graphs. So if I have a tuple of permutations, sigma 1 up to sigma d, it gives rise to an edge-labeled directed graph. This is, well, in short, it's the graph of an action of the free group. And in more details, it's a graph. The vertices are 1 up to n. Yes, when the permutations are permutations in the symmetric group on n elements. The edges which are directed, go from each vertex x, which again is a number from 1 to n, to sigma I applied to x. So I have d outgoing edges per vertex. And each such edge is labeled by a number from 1 to d, indicating which permutation I used to get this edge. Yeah, so x to sigma 1 of x will be labeled 1. And equivalently, this is the graph of an action of the free group on n elements through the homomorphism from the free group to the symmetric group, given by assigning those permutations to the generators of the free group. And this actually establishes bijective correspondence between tuples of permutations and graphs. More accurately, tuples sigma 1 up to sigma d of permutations on some n elements, and directed graphs on the elements 1 to n with labels 1 to d on the directed edges, and each vertex having exactly one outgoing and one incoming edge per label. This is the combinatorial definition, the equivalent of what it means to have a set with an action of the free group. And each such graph, naturally the free group acts on it. If I want to go the other way around, if I have such graph and I want to get the permutations, well, just if I want to get permutation number 3, I just focus only on the edges labeled 3, and I get some graph which is a graph of a permutation. So this is why it's a bijective correspondence. But now in this language, I have more. It's completely equivalent elementary, but I have more tools to deal with this problem. So consider again this group, the group presented by my system of equations. And I denote by good of x. Yes, when x is such a graph, good of x is going to be a subset of the set of vertices. Which vertices are included in good of x? All those vertices where you start from the vertex x, you walk the path dictated by the word wi, and you get a loop. You return to x. So this is what I call a good vertex. And I say that the graph x as a whole is 1 minus delta good if the set of good vertices is almost all of x, is at least a 1 minus delta fraction of x. And the following equivalence is elementary, that x is 1 good, namely that every vertex is good. From every vertex where you start and you walk the path dictated by a relation, you get a loop. This is the same as saying that this graph is not only a graph with an action of the free group, but with an action of G. Or in other words, that the graph X is isomorphic as a label-directed graph to a union of Schreier graphs of G. Yeah, so this is completely elementary, but very useful. So using this language of graph, I got this notion of a graph which is almost good, almost has an action of G. And I quantify it. I have 1 minus delta good graphs. So I can say what being locally testable means in the language of graphs. The group G is locally testable if and only if for every epsilon there is delta, such that every 1 minus delta good graph can be made 1 good by changing only an epsilon fraction of the edges. Yeah? So it's the same thing as we had in permutations. For every epsilon there is delta. It starts the same. Now instead of saying almost solution, delta solution, I have a 1 minus delta good graph. And instead of saying that there is an epsilon closed solution, I say that there is an epsilon closed good graph. Okay, so this is my goal. And a priori, well, in some cases, it may be that I have this graph, and almost all of its vertices are good, but whenever I try to fix, I have some vertex which is not good, a path which should be a loop does not close around it. I try to fix it, maybe I ruin something else. Maybe I try to fix it and I'll ruin something else then. So this is not something which should always be true. And I'm thinking of such almost good graph as a challenge that I need to solve. And solving this challenge is exactly changing just a really small part of its edges, so it becomes a union of Schreier graphs of G. Okay. So the first thing that we need to understand is where do challenges come from? Or at least to have some examples of generating challenges for a given group G. Then we can try to solve some specific examples, and then try to generalize to a general case of how to solve all challenges. So here is one particular way to generate challenges for an amenable group. Yes, always finitely presented, but in this slide also amenable. And here's the slogan of this one particular way to create a challenge. Take a finite subgraph of the Cayley graph with very small boundary. And in more details, well, I'm assuming that the group is amenable, so I take an epsilon Fellner set that is a set with boundary to volume ratio less than delta. Boundary of a set for me is the set of edges going from the Fellner set outside. So this is a subset of G, but I can also think of it as a subgraph, adding all the edges which go from F to F. This subgraph has almost all edges internal. It means that only edges which are adjacent to the boundary have less than the outgoing edges. And I can fix this F. I can add edges arbitrarily to make it a graph which has every vertex with the outgoing edges and the incoming edges. And then this is a one way to get a graph which is almost good. Almost all of the vertices look like they looked in the Cayley graph because they are not near the boundary, so nothing has changed. In the Cayley graph, of course, every vertex is good because it's a Cayley graph of G, so every loop that should be closed in G is closed there tautologically. And this F approximates this property. So this is a way to get a challenge. And I call this particular kind of challenges by the name Cayley challenges because they come from the Cayley graph. And I'd like to emphasize that this is not the only kind of challenges, but first we'll start with showing how we can try to solve these challenges, how we can try to take such a graph that was created this way and change it just a bit so it becomes a real union of Schreier graphs of G, a real good graph with an action of G. So here's a theorem. The Cayley challenges of G are solvable. I'll say what it means formally in a moment. So the Cayley challenges are solvable if and only if G is residually finite. Yes, so remember that local testability, even among amenable groups, is not equivalent to residual finiteness. But this is a weaker notion where I'm only required to solve the Cayley challenges, and this is equivalent to being residually finite. Remember that I'm only talking now about amenable groups. The notion of Cayley challenges was only defined for amenable groups. So this result of being able to solve the Cayley challenges equivalent to residual finiteness, it was first proved by Arzhantseva and Paunescu with first a different language and then a different proof. They call it this ability to solve the Cayley challenges weak stability, or maybe we would call it also weak local testability. And they prove exactly that an amenable group is weakly stable if and only if it's residually finite. So I will not give their definition, their language, but it's just this, the ability to solve the Cayley challenges. Here is what I mean more precisely when I say solve all Cayley challenges. I mean solve them in a uniform way. Yes, just that for every epsilon there is delta, such that every 1 minus delta good Cayley challenge can be made 1 good by changing an epsilon fraction of its edges. So if I remove the word Cayley, this would be just local testability, and this word Cayley here, restricting only to those specific kind of challenges, makes our life more easy, and that's why I call it a toy version of local testability, but it's worthwhile starting from this. So in this talk, I chose to focus on positive results. So in the next few slides, I'm going to show you why the implication from right to left works, why every residual finite group, an amenable one, we can solve all of its Cayley challenges in this precise manner formulation. And the tool that I'm going to use is Ornstein-Weiss quasi-tiling. I'm going to explain what it is. And the way that I'm going to use it is in the style of the way Alex and Szabo use it in proving a theorem characterizing amenable groups using homomorphisms in the universal Sophie group. But I'm going to keep it entirely combinatorial. OK, so here I will be giving you the recipe for solving Cayley challenges. There will be something small missing, and we'll address it in the next slide. So X is a Cayley challenge, a graph which I created as I showed you before. I took the Cayley graph, and I took a Fellner set out of it. Now take some radius R. It's a radius in the Cayley of balls in the Cayley graph, so it's a natural number, and fix it for a moment. And take some delta, which is very, very small, as some function of R. Now take a good Cayley challenge, and 1 minus delta good Cayley challenge for the group G. Then the observation is that since it's so good, since the relations are kept in almost all of the graph X, then almost all balls of radius R in X look like balls in the Cayley graph. Yeah, so this is not hard to prove. Yes, that being good just means that locally the relations look good, but if I'm a point which has a very big neighborhood where all the vertices are good, then if the neighborhood is large enough, then the entire ball around the vertex looks like it lives in the Cayley graph. OK, so I have a graph which locally almost all balls look like in the Cayley graph. Now I'm starting the Ornstein-Weiss quasi-tiling mechanism. I am placing an epsilon Fellner set in each ball. So let me draw it. I have this graph X, and it has some bad vertices, but almost all of them are, almost all vertices are good. And then almost every ball looks like it lives in the Cayley graph. Yes, I don't have, the balls are not disjoint, of course. And then I look at each such ball, and I place a Fellner set, a set with very small boundary. And this is a Fellner set of the group, and I can do it because, well, this ball just looks like it lives in the group. But I do it in every ball. So in particular, I'm going to get a lot of overlap between those Fellner sets. Yes, because let's say this is not good. Okay, so I'm going to get many, many Fellner sets with a lot of overlap. So we are in this stage. We covered almost all of the graph with Fellner sets, but with a lot of overlap. And then the next stage is to take a maximal, almost disjoint subcover. So it would make sense to pick of these Fellner sets a maximal disjoint subcollection, but it turns out that taking really disjoint subsets may disqualify too many sets, but I can take a maximal almost disjoint subcover. Almost disjoint means, well, a set of sets will be almost disjoint if I can shrink each set a bit, and then they become pairwise disjoint for real. So this is what I do. And now, after I took an almost disjoint subcover, well, it turns out that I'm no longer expected to cover almost all of the graph as before, but I still cover a constant fraction of the graph. I cover a constant fraction of the graph, and by sets which are almost disjoint, and they are still Fellner sets, so they also have very small boundary. Now, well, if I can cover almost all of the graph, if I can cover a constant fraction of the graph, then I can repeat this procedure, this time with smaller Fellner sets, and cover another constant fraction of the graph. And after several iterations, I'm going to cover all of the graph with Fellner sets, which are almost disjoints from each other. So this mechanism allows me to take a Cayley challenge and cover almost all of it by Fellner sets with almost no overlap. This is an instance of Ornstein-Weiss quasi-tiling. How is this related to solving the challenge? Well, here's an observation. If each of those Fellner sets is almost isomorphic as a graph to a finite Schreier graph, then we have solved the challenge. Yes, I'll draw this too. So this is X, and I covered almost everything with those Fellner sets. And I'm thinking in my heart of z squared, just when I'm drawing. Yes, the statements are general, but when I'm drawing, I'm thinking of z squared. So each Fellner set, if I use squares in particular, then not only does it have small boundary, but I can glue the boundary, glue in the trivial way, left to right, up and down, and then it becomes some kind of like a discrete version of a torus, and that's a Schreier graph of z squared. So after I covered almost everything about these Fellner sets, if each Fellner set almost looks like a finite Schreier graph, then by only changing the edges of the boundary, I can make this graph a union of Schreier graphs. So this is a very small change, and that's why I say that I solved the challenge. In the drawing, I disregarded the fact that there is small overlap. It doesn't really make a very big difference. So all that remains is to have a supply of Fellner sets, which are not only Fellner sets, not only with small boundary, but also almost isomorphic to finite Schreier graphs of the group. So in general, Fellner sets do not have to have this property, but for residually finite groups, by a construction of Benjamin Weiss, we have such Fellner sets. So his paper is a paper about monotileable amenable groups. Well, I don't really care in this problem about monotilability, but one of Benjy-Weiss's constructions gives us, for every residually finite group, a Fellner set with exactly this property. This property, which we trivially have for squares in Z squared, every residually finite group has it. So this is the way, and I can solve every Cayley challenge for every amenable residually finite group. But local testability is harder than that, because not every challenge in the world is a Cayley challenge. And the immediate example is taking Schreier challenges. Yes? Instead of taking, looking at the Cayley graph and cutting a Fellner set from it, I can look at a Schreier graph of some quotient or coset space and take out a Fellner set from this Schreier graph. And then I will get a challenge just the same way I got from, I built the Cayley graph. This is just analogous. So it is necessary, but it's not immediate that it's sufficient, to also solve all the Schreier challenges of the group. I'm going to talk about it and at least convince you why solving all the challenges is hard. Even, let's focus in the first part of this slide on abelian groups. So all of those Schreier challenges are in fact Cayley graphs of quotients, because abelian groups, every subgroup is normal, so I don't really have coset spaces. They're just groups. So fix some specific subgroup and look at G mod H. Okay, this is a quotient. So by the algorithm that I presented, we can solve all of the challenges coming from all of the Cayley challenges of the quotient. We can solve it by the algorithm that I mentioned. Yes, because it works for every residually finite group, and this quotient is still residually finite. I'm in amenable groups, and it's a group, so I can solve it using the Ornstein-Weiss quasi-tiling with the spatial tiles supplied by Weiss. But this, as its own, is not enough to prove local testability, because it is necessary not only to solve the Cayley challenges coming from each quotient, because if I only do that, I get an epsilon delta dependence for each quotient. But I have to have a uniform epsilon delta dependence running over all quotients. Yeah, so this is this point. To prove local testability for a group G, I have to have a uniform epsilon delta dependence running over all the quotients of G. This is one difficulty in extending the quasi-tiling method. Here's another difficulty, that if G is not abelian, then we may have subgroups which are not normal, and then G mod H is not even a group. And then it is not immediate that we can apply the Ornstein-Weiss quasi-tiling mechanism, because it was defined for groups. So these are two separate difficulties in solving all challenges. First, we must do it uniformly. Second, if the group is not abelian, then it's possible to have coset spaces which are not groups. Okay. So our work, what we did to prove positive results, is to define an object called a local testability system. And the point is as follows. If you can prove that a group has a local testability system, then the algorithm I presented generalizes to solve all challenges for G, not only the Cayley challenges, but all challenges in general. And this by definition means that G is locally testable. Just for some context, this relies heavily on G being amenable. I didn't have to write amenable here because having a local testability system would imply amenable. But this is something which is relevant only in the amenable category. Okay. So before I tell you what a local testability system is, I want to explain what it does. So consider a 1 minus delta good graph. That is a challenge. But now I'm not assuming anymore that it's a Cayley challenge or anything specific, just a general challenge. So this is the real problem, to solve a general challenge, a general graph where the relations are satisfied almost everywhere. And now, similarly to before, almost all balls of radius r, yes, first fix a radius r, then take delta very, very small, almost every ball embeds in a Schreier graph. But in Cayley challenges, I could say that almost all balls embed in the Cayley graph. But here, each ball embeds in a Schreier graph, and different balls may embed in different Schreier graphs. Yes, I may have some mix of Schreier graphs. It's even possible when I have only 1 minus delta good graphs, not real good graphs, but almost good graph, that something that locally looks like one Schreier graph gradually merges into something that looks like another Schreier graph. Yes, the structure here is much more wild. And OK, so we have a graph, and almost every ball looks like something we know, looks like something that lives in some Schreier graph. I want to repeat, to use again this algorithm. So how am I going to do it? In each such ball, I want to place a tile, like I did here. So someone needs to supply the tiles for me, and the local testability system is what supplies the tiles. The tiles, which are, on one hand, Fellner sets, they have small boundary, and on the other hand, you can glue the boundary to get a finite Schreier graph. So just a reminder that in Cayley challenges, the tiles supplied by Weiss, they worked. But we need something that works for all Schreier graphs of the group and in a uniform way. OK. So in the next slide, I'm going to define what a local testability system is. But first, some notation. So I have this fancy X with a dot. This would be the set of pointed transitive G sets with finitely generated stabilizers. So giving a pointed transitive G set is just like giving a subgroup. It's just like giving the stabilizer of the distinguished point, but it is more comfortable to speak in the language of G sets. Another notation is that I have the finitary power set. If I have a group, then P fin of the group is the set not of all subsets, but only of finite subsets. Okay. These were two notations. And now a definition. The local testability system is going to be a function that takes a positive real and a pointed G set and gives me something. Just concentrate on the domain for now. What is a local function? A local function is a function that only depends on a ball of some fixed radius. So my function f takes a real number, positive real, and a pointed G set. So let's concentrate, fix some epsilon, and concentrate on the mapping that takes a pointed G set to this function of this fixed epsilon and the pointed G set. So this is actually a function from pointed G sets to something. When will I say that this function is local if, in fact, it only depends on the ball in this G set around the distinguished points of radius r for some constant r. Yeah, so it's not really a function of the G sets whenever I fix epsilon, but only a function of some ball in the G set of constant radius. So here's the formal definition that such function is local if for every epsilon, yes, so fix epsilon. Now it's only a function from G sets to finite subsets of G. If for every epsilon there is a radius such that if two G sets have isomorphic balls of radius r around the distinguished point, then the function gives the same value. So it's only a function of the ball of radius r. This is a local function. Okay? Local because it only looks locally around the distinguished point at some fixed radius. Note that this in particular means that the image, when epsilon is fixed, the image is finite because it's only a function of how the ball of radius r looks, and we only have finitely many options for how a ball of radius r looks. Yes, because we have a finite number of generators, so combinatorially there are only a finite number of options. And now I can tell you what a local testability system is. This is what we're constructing. This is once we can construct this for a group, we know it's locally testable. So a local testability system is, it takes a positive real, which is the epsilon, and a G set, and gives me a tile. Yeah? So here, this is how it's used. I have some graph, and here I have some point, and the ball around it looks like it lives in some Schreier graph. And then to get the tile that I'm going to be using in this ball, I ask the local testability system which give me the tile. So I tell the local testability system, this is my epsilon, and I have a ball which lives in this Schreier graph. Give me a tile. Giving a tile is like giving a finite subset of the group. So what do I require from a local testability system? First, Fellner's condition. The tile must have the ratio of boundary to volume must be smaller than delta. Second, I want the tile to be almost isomorphic to a finite Schreier graph. So if you think about it, it just means that this tile, yes, the T is the value, is what the local testability system gives me for this epsilon and G set. So being once you have a very small boundary, it turns out that being almost isomorphic to a finite Schreier graph is just like being a transversal for the cosets of some finite index subgroup. Yes, like a square and an n square, it has small boundary, and it's a transversal for the cosets of n times z squared in z squared. So these are the two conditions which we actually already talked about. Small boundary and looking almost like a finite Schreier graph. The second condition is that f must be local. Yes, this is what we said before. Every time you fix epsilon, then this f doesn't really look at the entire G set, but only at a ball of some bounded radius. This localness is what allows me to have a uniform epsilon delta dependence. It makes life much harder, but this is what allows me my mind, only solve each challenges coming from each Schreier graph separately. But if I do it in a local way, then I actually get a uniform epsilon delta dependence. These are the two important conditions. There is another technical condition, which I will not spell out. I'm just writing it here for future reference. But this technical condition, if you remember in the Ornstein-Weiss quasi-tiling, I had this stage where I chose a maximal almost disjoint subcollection, and I claimed that it covers a positive fraction of the graph. So this is just some technical condition that ensures that it really does happen, that I really do, in each iteration of the algorithm, cover a positive fraction of the graph. So this is a local testability system. And now I tell you when we can build it. Okay, so we have constructed those local testability systems in the following cases. First, for abelian groups. So this implies that the algorithm works for abelian groups. So the abelian groups are locally testable, and this recovers the theorem of Arzhantseva and Paunescu. Moreover, yes, the reason that we define this is that we can generalize it to bigger classes of group. So we can also build this for nilpotent groups of class 2, so classes 1 and 2. Actually, we cannot really do it for nilpotent groups of class 2. We can do something a little weaker, which is still sufficient. This is maybe this weak version of local testability. Maybe it's the deepest part of this theory, but I will not talk about it now. And also, we build it for Baumschlag-Solitar 1, 2. So just remember, this is a solvable group, which is not polycyclic, but we were able to build a local testability system for these two. And this result about finitely generated nilpotent groups of class 2, it's actually, I really strongly believe that we'll be able to do it for all nilpotent groups. I'll tell you more. Actually, the situation now is that we already have a construction of a local testability system for all nilpotent groups, but only a proof that it really is a local testability system for class 1 and 2. So we already have a suggestion for a construction for this object for all nilpotent groups, but only a proof that it really works. It really is a local testability system for the low classes. And just a reminder, we don't expect to build local testability systems for all solvable groups because we know that not all solvable groups are locally testable. So the constructions for Baumschlag-Solitar group and nilpotent groups, they are hard. They rely on some groundwork, which is not specifically related to local testability that we made on the geometry of these groups. It's hard, especially when you try to treat nilpotent groups. But there are some different difficulties in Baumschlag-Solitar. So I will not have time to talk about this. But I do want to show you how to construct the local testability system for abelian groups, but not in the most direct way, but in a way that hints what needs to be done for those more complicated classes of groups. So I'll go back to the definition of a local testability system. So we need to define such function, taking epsilon in a G set and returning a tile. And I'll start by fixing epsilon. So epsilon is how well we're required to solve the challenge, how many edges we are allowed to change. Now we have this mapping taking a G set. Yes, this is a pointed transitive G set. So it's actually G mod H and the distinguished point is just the unit, I can write every pointed transitive G set like this, I will take my group G to be the free abelian group. Okay, so I'm only focusing now on building those systems for abelian groups. For each such G set, I have a tile, let's call it T of XX. This is a tile which it has a small boundary and it's almost isomorphic to a finite Schreier graph. Almost isomorphic to finite Schreier graph. Who gives me this mapping? Well, either I do it explicitly, it's not very hard to do for abelian groups, or I use the general theorem of Weiss, which tells me that those tiles exist. So explicit or Weiss. The problem with this mapping is that no one promises me that this is a local mapping, that epsilon is fixed. Then I'm only allowed, when computing this mapping, I'm only allowed to look at the ball of some constant radius. So how do I ensure that this is local? For abelian groups, it's not that hard. How to make this mapping local? So I call it the greedy algorithm. First, try the tile of ZD mod 1 So this is a particular G set, the G set of the Cayley graph. Yes, this is just T of the Cayley graph. Okay, which was supplied to me there. What do I mean try? See if this injects into this G set. If this G set locally looks like the Cayley graph, then this tile will just fit there. If the tile doesn't fit, so I'll call it if it fits, use it. If it doesn't fit, yes, if I try to put it on to place it on the G set and I see that the geometry of the G set just doesn't look like the Cayley graph, so this is what I call otherwise. If it doesn't fit, then it means that I found some short elements in the stabilizer of the distinguished point. Yes, because not fitting means that I found some cycle. So otherwise, we found short elements in the stabilizer in G of the distinguished points. And then they generate some subgroup H, and I can try this process again, but now not assuming that I'm in the Cayley graph, that X locally looks like the Cayley graph, but assuming that my G set locally looks like G modulo this subgroup generated by those short elements. And then I have a tile for this group as well, and I try it. I try to see if the tile of G mod H fits. If it does, I'm done. If not, then I repeat this process again. Now, this process is guaranteed to finish in a bounded number of steps because each time I either decrease the rank of the group or I decrease the torsion, the size of the torsion. And this makes this function local. So this is essentially one way to build a local testability system for abelian groups. And I just want to emphasize two places where I use the fact that it's abelian. First, I saw those short elements in the stabilizer, and then I took a quotient, but I assume that I still have a group. So this is one place where I said, OK, the H is normal. Immediately, I don't have to check it. So I can go to the group G mod H and not a coset space. And second, here, when I use the tiles supplied by Weiss, then he supplies tiles for me only in groups. So even here, I use the fact that every G set is the Cayley graph of some quotient. Working around these two problems is the main thing that I do. And this will be, I think, a large part of the paper. But this is for another time. Thank you.
Any questions?
Is there some chance to use it for groups which are not amenable but approximated by amenable in some sense?
I try to think about it, and I'm pessimistic about this outside of the amenable world, even a bit outside. At least not if you want to really prove local testability. Maybe you can prove something a little weaker with some weak dependence on the size of the permutations. But if you really want it not to depend, well, I try to think about it, and I'm pessimistic about using this method as it is.
Have you thought about the three-dimensional solvable polycyclic group at all? Seems like a good next example to check.
Mm-hmm. Yeah, so the Bauschlag-Soliter group, solvable, it's just taking H and N extensions twice. And the important groups of class 2 is, again, you can think about it as, well, not really here, but let's say the Heisenberg group is, again, it's three times. What I want to say is that if you take H and N extension twice, and polycyclic groups of class of doing twice is just a specific definition of it, then everything is really tame, but the third time, things go wild. So this is why I don't yet know about rank 3, Hirschfeld 3. But yes, certainly after we finish the important groups, this is what we'll do.
If there are no further questions, then let's thank the speaker again.